Any other questions or anything before we get going? Did anyone, like, who watched that video I sent? I thought it was pretty fun, right? And that is a really good example of an evolutionary algorithm. If you haven't watched the video, watch the video. It's fun. There's a lot of, like NEAT, it's called, neuroevolution something something. It's been around for a little bit, and it effectively combines evolutionary algorithms and artificial neural networks. And it's been used a lot for things like games and whatnot, which is a lot of fun. And I was talking to another student about this today too, but another student who I won't point out, who I won't single out, kind of made a comment though about, and I'm picking on them not because they're wrong, but because they brought up a really good a point of discussion. Is like they made a comment about like the video game aspect of that video. All right, where like the comment was, it wasn't so much about the evolutionary algorithm thing, but I think this is like a good point to make. It's not like the comment the student made was like, yeah, okay, the video game thing, but like, I mean, I don't know how to make a video game, so like that's like, it's cool, but like, you know, it's unrealistic. And I'm like, that's nonsense, because if you've never made a video game before, obviously you don't know how to build the thing that you want to build before you build it. Like what a ridiculous, like obviously, but imagine being like, well, I don't know how to do that thing I want to do, so I guess I can't do it. What? Come on. Like think back to like the tic-tac-toe assignment. Oh, I didn't know how to make like a game loop in tic-tac-toe, but you had to do it for the class, so you did it. You can do it. You can do it. You absolutely can do it. Don't sell yourself short. And I'm not saying this is a rah, rah, rah. I mean it as like a, no, you absolutely can do this. Like, don't tell me you can't. I know you can do it. You're capable. No one knows how to build anything that they've never built before they build it. You just figure it out and you do it. And is it gonna be good the first time you do it? No. That's fine. That's every software engineer's experience. You write code. You write more code, you get better and better and better and better and better. Remember, I always talk about this in like 161 and 162, and like I talk about it in the context of like efficiency in your code. And I'll say things like, sometimes good enough is good enough, right? Like, oh, could we make it better? Yeah, but it doesn't matter. Good enough is good enough. The same thing also goes with like your code. Obviously, you want to have good quality code. You want it to scale well. You want all these design principles that you want to use because you're like a good programmer. But don't let those things distract you from just getting it working, okay? Obviously, you want to do it good, obviously, but don't get so hung up on like, does this scale? Should I refactor this right now? Can that be a get it working? Refactor later. It happens, whatever. It's fine. It's fine. And if you make a little video game for a course like this just to run neat for the hell of it, it doesn't need to scale well for the future. It's fine. You just need to do it, and you learn something. So no one knows how to build anything that they don't know how to build before they build it, obviously. So don't let that discourage you from doing it, right? Hopefully that's obvious, but isn't it kind of funny how you, like I have to tell myself that too sometimes. And it's obvious, but yet I have to remind myself, well, just do it, right? Now that doesn't mean like, oh, well that means I can go, make Twitter overnight. Obviously you can't, like, no, come on. But the point remains, just go and try, go do it, see what you can do. Then you'll figure it out.
I turned this speech into one of those hope core videos. You know what that like?
What's that?
It has, you know, it's like this. It just shows this kind of montage of a bunch of like panoramas of like various just like nature environments, and then it's just like the text. The text is from the screen, and it has this like whimsical little sound effect in the background.
Okay, look, I'm really not trying to be that corny. If I came across that corny, I'm sorry. I really didn't mean to. But just remember, you can do it. Just do it. That's all. All right. Anyways. Okay. All right. So last time we were talking about problems, and we really broke down like thinking of problems in terms of like functions, right? Some input, some model function, whatever you want to call it, output. And then we were talking about optimization problems, and we used TSP as an example, which is a great example to use because it's like assignment 1. So TSP, traveling salesman problem, it's a classic optimization problem. I pull this straight from Wikipedia. TSP can be modeled as an undirected weighted graph, just a basic graph, such that cities are the graph's vertices, paths are the graph's edges, and the path's distance is the edge's weight. It is a minimization problem starting and finishing at a specified vertex, specified city, after having visited each other vertex exactly once and only once, except the first and last city, because it needs to be the same one. Effectively, the problem is find the shortest Hamiltonian cycle within a graph. Okay? So here would be a very simple version of that problem. We have 4 cities. What's the shortest path to visit all the cities? That would be the game we're playing. If you're thinking, well, that's not too bad, well, that's not too bad, but turns out this is a really friggin' hard problem to solve, like provably so. I forgot to talk to Taylor and be like, how do they not know what NP-hard is? But whatever. So to think of this in terms of those 3 parts of that system I was talking about, input, model, output, the Hamiltonian cycle, the order in which you visit those vertices, the cities, is the input. The model is really simple. Sum up the weights in that order. And then the output is the total distance. And what do I want? Well, I want to find the input that gives me the smallest output. That's it. It sounds simple because it is a simple idea. Now, the problem is tricky. The optimization problem is tricky. But in terms of that process of taking a path, finding the weight, or the distance, and then getting it, that part's simple. All right, but this is just a description of the system, not the description of the optimization problem. Just to frame this as an optimization problem, find the cycle such that that has the smallest distance. Turns out that is what's hard. Finding a Hamiltonian path, easy. A, B, C, D, done. Finding the best one in terms of minimizing the distance, very hard. So there is a trivial algorithm to solve the instance of the problem, though. Turns out that, technically speaking, the algorithm, and I've talked about, if you've had me before, I've probably talked about this before. I use this example a lot to describe like hardness. So it's trivial to actually find the best path. The algorithm, at least. Find the length of all possible Hamiltonian cycles. Pick the shortest one. Do you agree that that would give you the shortest one? Try them all, find the smallest. That's the smallest, obviously. Now, okay, yeah, and given a set of vertices V, the computational complexity of calculating a cycle's length is, well, the size of that set, right? Though it's really a matter of just applying a linear search to each of those cycles, but where does the problem arise? Well, it turns out there are a lot of different possible Hamiltonian cycles for these problems. And as the input grows, as like the number of cities grow, the number of possible cycles just it grows catastrophically. Some of the worst scalings we can get that we know. So here's things to remember. Often the starting and ending city is fixed. Always start at city A and end at city A. Now, the choice is arbitrary because if you think of a cycle, if the cycle is like A, B, C, D, what's the difference? And D implicitly goes back to A. That's the same as like B, C, D, A, right? I'll show you in a second. So given the 4-city problem, how many cities are there that could be visited next? I have 4. Let's say A is fixed. How many possibilities, like how many choices could I make right now? 3. So let's say I go to B. I could have gone to D or C, but let's say I go to B. How many remaining choices do I have? And let's say I go to C. How many remaining choices do I have? Right? Okay, great. Now, if you're paying attention to the pattern, turns out it's like a factorial. Okay? So, yeah, so therefore there should be a total of 6 possible cycles. 3 times 2 times 1, which is the same as 4, which is the number of vertices, minus 1. Now, why minus 1? Well, because the first one is fixed. Okay? If I said pick any city to start with, well, how many choices do we have? 4. 3, 2, 1. So, okay, it would be more if you could pick, but then again, that part shouldn't matter. I'll show you what I mean in a moment. All right, so here's all of the paths. Now, you might notice, though, that half of these cycles are just the reverse of another cycle. Okay, so when the question is, how many possible paths are there? You might notice that A, B, C, D, A is the same as A, D, C, B, A. This and this are the same. Meaning, like, because the direction doesn't matter. It does not matter in terms of the total distance, assuming that the distance is both ways. You could, exactly. If it was a directed graph, which there are variations of this problem that have directed graphs where maybe the weights are different, well, that's a completely different story. But in this general case, that's what we're looking at. So, you know, we could generalize this to be like, well, okay, it's going to be like the cardinality of the set of vertices minus 1 factorial divided by 2. Because for every path this way, there's the reverse, right? For every one where it says go A, B, C, D, there is the one that goes in reverse order. So just get rid of half of them. There, great. So how many possible cycles are there for 100 cities? Well, a lot. Some number times 10 to the 150, that's a lot of zeros. Okay? In fact, I always love to do this as a point of reference. There are about 10 to the 26 atoms in the Milky Way. What I mean by that is, if I took every possible Hamiltonian cycle that's valid, even excluding, I mean, this whole half does nothing. The fact that it's, but divided by 2, that has like no effect. Oh, okay, great. Instead of 9.12, whatever, times 10 to the 155, it's 4 times 10 to the 155. The 155 zeros is the problem. Okay, not the 4 or the 8. Sure, don't get me wrong. I'm going to be happy that I have half of them to look at, I guess, but it's about like, where's the problem, right? So, if I were to take every atom in the Milky Way and assign it one of the cycles of 100 cities that are valid, I'm going to run out of atoms hilariously quickly. That's wild. Like particles in the universe. It's wild. Humans are terrible with numbers like this. Right? So I do my best to try to make it clear how, like, okay, this sucks. The algorithm is simple, but it's not practical to look at them all. If your computer is super fast, how many, let's say, like let's play a stupid game, all right? Let's just do like 1 times 10 to the power of 155, okay? So we got a big number. Now, let's say we have the world's best supercomputer that can evaluate, like look, evaluating one of these paths is linear time, okay? Now we're saying like n is 100, that's actually a small number, right, in terms of like the linear time computation to look at n things, that's tiny, right, that's nothing. So let's say we have a world's amazing supercomputer and it can evaluate a quadrillion a second. Does that seem, that's a good computer, right? Would we agree? It's kind of unrealistic to expect a computer to do that today, but let's say we can do that. So let's take that value and divide it by a quadrillion. So that's like, okay, 1,000, million, billion. No, 9, oh no. It wouldn't have mattered. All right, one, okay. 1,000, million, billion, trillion, quadrillion. Let's make it quintillion for fun. Oh yeah, I mean, obviously, all we're doing is eliminating a couple of zeros. It doesn't matter. Let's say let's take that number and divide it by, let's say somehow we have a septillion of these computers on the planet right now. 1,000, million, billion, trillion, quadrillion, quintillion, six, whatever, septillion. Let's go to like 8, 9, 10. Whatever like 10 of those are. Like, yeah, great. Okay, right? So like that's seconds though, right? Let's pretend that's how many it could actually do every millisecond. Look how long. Do you see how long it was taking Google to be like, right? Obviously that's not helpful. So that's how many milliseconds. So okay, let's say that's how many milliseconds are there. So milliseconds. Okay, let's just go, because that would be the number of seconds. So 60 seconds in a minute, 60 minutes, 24 hours a day, 365 days, 365 days a year. That's how many years. How long has the universe existed? Yeah, 13 point, let's call it 20 billion because scientists were wrong. It's actually 20 billion, let's say, so let's divide that by 20 billion. That's how many like existences of universes we would need to do this on unrealistic computational systems. The point I'm making is it ain't gonna happen. Remember when I was saying like we use like computational intelligence for hard problems? Yes, there's a hard problem. Turns out there's actually some nice good approximation algorithms for something like TSP. TSP is a very well-studied problem. So you really actually probably wouldn't want to use an evolutionary algorithm for TSP, not because of how hard it is, but because of how crazy people are at already coming up with good solutions for them, but that's another conversation. The point is, it's freaking hard. I don't care how good of a programmer you are, you're screwed. So, whoop. Okay, don't need that anymore. All right, okay. Let's forget about TSP for a second. Here's one, N queens. Familiar with N queens? If not, I'm going to explain it. It's fine. Here's the problem. Now, you'll notice N queens is a slightly different variation of like an optimization problem. Really, it's not even an optimization problem. It's kind of like more of like a binary problem, but we can turn it into an optimization problem. You'll see what I mean in a moment. So, N queens, all right? Who here does not, and be honest, who here does not know how to play chess? Okay, here's the thing about queens, okay? Queens can move this way, like I'm looking at this one. It can move this way, and it can move diagonally. All right? That's what we've got. So, the goal of N queens is, on an N by N board, a typical chessboard is 8 by 8, but we can play whatever game we want. On an N by N board, place N queens on that board such that they could not possibly like attack each other, right? So see how like none of these, and right now we're doing like a depth first search of like possibilities of the N queens. That's what we're visualizing here in this GIF. So we want to place these queens, like see how like here, okay, these queens can't attack each other, right? You can't make that one and attack that one in one move at least. So the goal is place N queens on the board on an N by N board and have them situated such that they cannot attack each other. That's the game. So unlike TSP, this is kind of like a different optimization problem because there's nothing really here to be minimized if we think of this in the most straightforward way possible. Because the question is this a valid board configuration or not? That's the question. There's nothing to be minimized. But we often do turn this into a minimization problem by saying, well, minimize, because you need like a gradient, right? If I keep saying like, is this valid? Is this valid? Is this valid? Like there's no way to learn,
No improvements
right? You want a gradient. You want to be able to be like, is this valid? Okay, no, but there were 3 queens attacking each other. Is this valid? No, but there were 2 queens attacking each other. Ooh, that's better, right? I want to minimize that all the way down to 0. That's the goal. How many board configurations are there? Well, for an 8 queens problem, that's like the size of your typical chessboard, that would be like 64 choose 8. Okay? I have 64 options, and I have to place 8 queens on there. How many different combinations are there? Well, there's only, there is, okay, 64 choose, this is the syntax people write in math for that type of stuff, right? If you've taken like discrete math or like combinatorics or something, who here has taken discrete math already? Did you talk about this stuff in discrete math? Anyone do we have combinatorics here?
Yeah, every other year.
Every other year. So like you recognize it. Cool. So there are 4,426,165,368 different configurations. But turns out there's only 92. I mean, I could say only. Oh, there's 92 valid configurations, which is pretty cool. There's no such thing in this particular problem. There's really not a best answer. It is one of 92 correct answers, which is pretty neat. But to generalize this, it would be n times n, or n squared, choose n. That's what we want. So as n gets bigger, this gets badder. And here's evolutionary algorithms, yeah, we could use something like that for here, as long as we got a way to add that like gradient, which we'll talk about. NASA's problems. There's a couple of things. See this structure here? That's what do they call that? Pardon? No, it's truss. It says it right there. Good. Right? Okay. This looks like who's seen something like this before, but on Earth, not in space? Of course you have, right? They're everywhere, right? Turns out, do I have a picture of it here? I do not. Oh man. See if I can find it. Why do I not have images? Here's some weird pictures, right? If I go down here, look at that. Does that look like, would an engineer design that? No. Why? Because that's ridiculous. Turns out that right there is what does it say? Like a bajillion times. Maybe I might need to find the paper. The point is, it turns out that some designs are way more robust against vibrations than what someone would typically design. And what's interesting here that I want to point out, actually here, I'll circle back to what I was about to say, but there's truss. See this? This is an antenna. Who here's seen an antenna before? Who here's seen an antenna that looks like this before? That's ridiculous, right? Turns out that antenna, which by the way is itty bitty, that's not big, that's tiny. Turns out that antenna is the best thing they have for certain signals in space and crap. All right? No one would have designed this. That is not what an antenna looks like, but for some freak reason, turns out it's good. So, turns out we, as humans, have preconceived notions of what good is. We know what trusses look like. Turns out we were wrong. We know what antennas look like. Turns out we were wrong. So another cool thing about evolutionary algorithms, if you do it right, and you've heard me say it before, and maybe you haven't noticed, and you will hear me say it again. We want to be careful about how much of our bias we add to the system. Think about even the starting population. I always say start with a randomly generated populations. And you might be like, well, we know what antennas look like, so let's start with randomly generated realistic antennas. We may have never found that one if we did something like that. So we got to be careful. Okay, so optimization, right? What is this as an optimization problem? Here's a design. Let's simulate how good it is or test how good that antenna is. What was its measurement? Keep iteratively designing and so on. Okay, all right. Modeling. We were talking about optimizing. Now we're talking about modeling. Modeling is this part. Writing software is modeling, okay? Sometimes it's a simple problem like write a program to calculate a grocery bill, okay? Input is the items. The model is add things up and add a sales tax or something. And the output is the bill, right? The actual number. Great. Sometimes they're simple, sometimes they're complex, like write a classifier to classify different irises, the different types of irises there are, right? Look at those pretty flowers. Well, it turns out, I guess there's 3 different main ones of these irises. Go write a classifier for that based on some measurements of them, based on like this length and width, because you can see they have different like lengths and widths, right? So maybe if we can make some observations of these pictures. By the way, this is a classic benchmark problem for like machine learning. It's classify the irises, and there's some neat nuances about it. The point is, if I were to say to you, here's a table of petal lengths, widths, and sepal lengths and widths and whatnot, write a classifier to tell me which one it is. And you're going to go, how many? Oh. Okay, if the length is greater than this, but less than this, but also not greater than that, and that, you're going to have to start writing this crazy complex code, right? And who knows, like I don't want to write that code, right? That's weird. That's tough. So what we do instead is we say, let's use a k-nearest neighbor classifier to see if we can figure this one out, right? That would be like modeling, where the model is, here's the inputs, here's its class. So we often use like machine learning and AI to do the modeling. Oh yeah, okay, so find the best classifier setup. For example, find a classifier model to classify the irises, the inputs, such that the error output is minimized, such that we get the best accuracy. So it's not the inputs that we're like searching for. We're not looking for the best input. We have the inputs. It's the flowers. It's the flower measurements. The goal is to find the model. Real world problems, well, like we all have brains. We don't know how they work. They obviously receive input. They receive output. Can we somehow like model how the brain's going to react based on the inputs and the outputs? For example, right? Like modeling is big. It turns up everywhere. And then finally, simulation. Turns out, if you want to know how a little island nation is going to react when a giant volcano catastrophe happens, we can't do that in real life very often. We like to simulate these things because no one gets hurt. So we like to simulate things. So simulation occurs when the inputs and model is known, but the output is unclear. And that's another thing we can do when thinking about these systems. So we have like optimization, we have modeling, we have simulating. They're all different ways to look at these systems, and clearly they have different focuses. But often, interestingly enough, we do like to reframe certain types of problems as like other versions of themselves. Like we will see examples of how we turn modeling into an optimization problem. Obviously, right? Where, well, you'll see. Okay. Any questions about any of that way we're thinking about it? All of this is like, all of this stuff, I assume you already know. You just haven't spent a lot of time thinking about it in this way. But I just want to make sure we've got this in our head going forward. And then a search problem. Well, we have some landscape of different let's say we're optimizing. Let's say we're doing something. We want to go and find the best, the hottest part in this room. Okay, I'm not worried about the third dimension. I'm worried about where's the warmest part in the room. Imagine this is a plot of where I physically am in the room, and this is its heat, right? We can agree there might be some hotter areas and colder areas, right? So sometimes we want to move through this space to find the hottest area of the room. And just because right here is really hot doesn't mean somewhere over there isn't even hotter. But that's the idea of this search space, this landscape. And we kind of talked about fitness landscape before, but we saw how fitness and the representation, like the encoding, were kind of tied and whatnot. But we're going to come back to that. All right, and search space is small enough, it may be entirely possible to enumerate all possible positions in that search space. It might be entirely possible. If you have TSP and you're doing like 10 cities, okay, go for it, have at it, find the best one. It's constrained enough, you're fine. But sometimes it's enormous or literally infinite, and we're in big trouble. Because remember, if you don't remember, if you've had me before, I know you know this, but I'm going to say it again. I'm talking integers. What comes after 1? What comes after 2? What comes after 3? How long can I keep going? Forever. Towards infinity, right? Now let's talk real numbers. What comes after 1? Yeah. 1 point. An infinite number of decimal places. 1.1, no, 1.01, but what about 1.001? Turns out, look, with real numbers, we've got the same infinity problem as integers. It goes on forever. But we also have like an infinite number of numbers between every friggin' number. And I don't mean between like 1 and 2, well, yeah, but I mean between like 1 and 0.1, there's an infinite number of numbers. And between 1 and 0.01, there's also an infinite. So turns out we have like severities of infinity. Okay, some infinities are scarier than others. All right, so when framing problems as search problems, we can, like you probably haven't thought of like TSP as a search problem. But turns out it's this high dimensional space, but we can move through this space looking for the best solution. And we're hoping maybe there's gradients, but the search spaces are often complex enough that, because we have like algorithms that are really good at following gradients, like a hill climber. There's a lot of algorithms that are really good at finding gradients. And if our problem is like convex or something, use the hill climber until you find the best one. Great. But we have these crazy complex search spaces, so we need algorithms that are good at traversing these complex search spaces. Gradients are helpful and all, but we need other mechanisms to be able to guide us around the search space. Okay. It also allows us to ask questions like, what is a good way of traversing this space? Can we change the search space? What can I exploit about the search space? Can I simplify the search space? When you really put a pin in like a search space as a thing, we can start to like make it a more concrete idea as opposed to this abstract space. Once we make it more concrete, we can start to, it becomes more accessible to think about these types of questions. And then optimization versus constraints, objective functions, like fitness functions in the context of evolutionary algorithms. Remember, the fitness is some measurement of goodness of what I want of a particular thing. It's the fitness of a robot walking. Well, the further it goes, the better. In that little video I sent out, the farther the doodle guy goes up, the better. And TSP, the smaller the distance, the better, right? We've got some fitness. A binary evaluation checks if it's good. I already told you this, right? Okay, sometimes optimization problems can have constraints. Consider TSP with the requirement that some city X is visited before some city Y. Entirely reasonable to have such a constraint. It's also possible that constraints, we can convert these things like n queens, well, no, minimize the number of attacking queens. That gives us a gradient. We like that type of stuff. I already talked about this. Okay, yeah. Further, it's sometimes possible to add constraints to an optimization problem that reduce the size of the search space, like in the example above, not looking at paths to go to work that are out of town, right? Obviously, going from my house to St. FX, of all the possible paths to go there, includes going through Tokyo. but that's obviously a bad idea. And I know it's obvious, but when you're talking about these things as these more abstract problems, we want to make sure like they're abstract, but we can tie them back to these concrete ideas. All right, hardness. For simplicity, a problem is easy if we have a fast way to solve it. A problem is hard if there is no fast solver. And in fact, we even say they are super duper hard if we have, maybe we don't have a, because there are some problems where, this is where it gets kind of like, there's some like nuance there. I'm saying a problem is hard if there's no fast solver for it. But sometimes, although there is no fast solver for it, turns out there are some problems that, okay, there's no fast solver, but if you give me a solution, I can tell you quickly whether or not that's the solution I'm looking for. But there are problems where, like TSP is NP hard. If the question is, do you have like a, TSP is NP hard, which means there's no fast solver to find the best one. But if someone says, no, 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 don't worry, I have the best one, here you go, I have no way to confirm it. Where there are problems where it's hard here and it's actually easy to verify, there are problems where it's hard here and you just also can't verify it very easily as well. So those are super duper hard. Continuous versus discrete. If a problem is defined in terms of continuous values like real numbers, it's called numerical optimization. These problems have uncountably infinite search spaces. That's what I was talking about, how many numbers are there between 0 and 1? A lot. If the problem is defined in terms of discrete values, then it is a combinatorial optimization problem. These problems can have finite or countably infinite search spaces, meaning there's an infinite number of them, but it's kind of not as bad as uncountably infinite. That would be like 1, 2, 3, 4, all the way towards infinity. Still not great, but not as bad as the uncountable stuff. But sometimes they have a finite number of search spaces, like TSP. There is a finite number. It won't go on forever. There is a finite number. All right, yeah, okay, a little bit more. Okay, class P problems are decision problems that can be solved in polynomial time. Polynomial time, when we say that, all it means is we have an algorithm that might look something like n squared. Hey, not too bad. Even like n to the 4. That's not bad. Polynomial time, we're happy with stuff like, can you see that reasonably well? Yeah, yeah. Right? Not too bad. Class NP are decision problems with positive solutions that can be verified in polynomial time. Really hard problem, but we could check pretty easily. I know this looks bad, and I know like you don't want an algorithm that's like this, but in the grand scheme of things, this ain't that bad. Okay, and then class NP complete is the decision problems with no known polynomial time algorithm. And it's funny, computer scientists are really, they're sticklers, and they'll say like, there's no known polynomial time algorithm because we haven't mathematically proven that there doesn't exist one. We just haven't found one. But we can verify them in polynomial time. So it's a super duper hard problem, but we can confirm in polynomial time that we're good to go. And NP hard is a decision problem with no known polynomial time algorithm and can't be verified in polynomial time, like the decision version of TSP. Yeah, okay. So what do we really need to know about hardness? Some problems are hard. They're super duper hard. And when we say hard, we actually are using it in like in a measured way. I don't just mean like, man, this test is hard. I mean like, no, this is NP hard, meaning good luck, kids. Right? It ain't gonna, like, good luck. Given this, the goal is often to find good enough solutions, though, to these problems, because finding the optimal solution is a fool's errand. It ain't gonna happen. So the tools like evolutionary computation are used in situations like this. So I'm pretty sure by the way, have you heard about that like P equals NP, right? Raise your hand if you've heard that before. Okay, it's kind of like this like joke. Like, oh, does P equal NP? I think P equals NP. I think they don't equal. Turns out we don't know the answer to this question. And this is tied to some very interesting mathematics where it turns out we can prove that there's stuff that we can't prove, which is kind of crappy. We have proven that there are some things that we can just never prove. We don't know what they are, which is super crappy. And it's funny, you don't have to go that long ago. Like a century ago, people thought like eventually we'll prove everything. But people proved that that's never going to happen, which kind of, I don't know, maybe that's like the spice of life. I don't know, right? But turns out there are things we can't solve. So this whole, does P equal NP? For all we know, we might never know. That doesn't stop people from trying. Good for them. If P does not equal NP, it just means like, well, all right, that's the way it is. There's just some freaking hard problems out there. But it is possible that some weirdo comes along in the future and goes like, wait a minute. If we think of this problem this way and we solve it that way, oh, we have a polynomial time algorithm to solve it. And the interesting thing about that fact is, by the way, it turns out that all problems, if you have an NP-complete problem, there's a lot of NP-complete problems out there, okay? Where it's a decision problem with no known polynomial time algorithm, but can be verified in polynomial time. If someone shows up and says, I found a solution to this one NP-complete problem, they've actually found a solution to every NP-complete problem. Why? Because it turns out that every NP-complete problem is the exact same problem. You just have to like turn it into one another, but you can turn every NP-complete problem into a variation of another NP-complete problem. Meaning if you can solve one, you can solve them all. And if you solve them all, you kind of, first, you'll win $1 million, and then everyone might hate you. I don't know. Maybe they'll love you probably long term, but for the time being, people are going to be mad at you because there's a lot of our world that kind of relies on the fact that there's some hard problems. Like when you log into your bank, you see that little like lock in your bar, right? You know, it's a secure connection. Turns out there's a really easy way to break that encryption. I mean, the problem is it's going to take orders of magnitude longer than the universe has existed to crack it, but there's a simple algorithm to do it, and it all relies on the fact that this is a hard problem. If someone says, actually, we can figure this out in polynomial time, all of our encryption is done. We're screwed. Okay? Then there's a whole conversation about like quantum computing. Well, maybe quantum computing makes some of this stuff moot. I don't know. That's a whole other conversation. Anyone who says they understand quantum computing is lying. All right, so here's some pictures that kind of show you like, I don't know, where's NP complete, NP, I don't know, whatever. All right? Neat. So at the end of the day, this is a conversation to have with Dr. Smith, not me. This is the conversation to have with me. There's some hard problems. Sometimes you need something like evolutionary computation. And when I say hard, I don't mean just like, this is hard. I mean, good luck. All right. Any questions about that? All right, cool. I will take a moment to re-emphasize something I said already before jumping into this, because this I kind of want to hit. I don't want to start and then have to stop in 5 minutes or 4 minutes or whatever. In this class, there's the assignments, right, where I give you something to do. If you just go and do what I tell you to do, you're not going to have a good time. It's like you'll do fine, but you're never going to get the point of this class if you just do what I tell you to do. The only way to get anything out of this class is to just try the weirdest, most crazy, fun things you can try and just see what happens. The weirder, the better. All I care about is you tried something interesting. That's where you can have fun. That's where you're going to learn the most about evolutionary computation. Okay? So if you sit down going like, oh, he tells me I'm going to do that, but if you sit down and say, write a GA TSP solver in ChatGPT, it'll do it like that. But that's like, okay, but that's, what are you doing here? So the assignments, I give you very prescribed things. And then there's the project. The project, everyone will do independently. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Perfect. 11, that's great. That'll be a little over 3 weeks, I think, of lectures, which is fine for the amount, like the course is designed around that. I want you, like if you're sitting down and be like, just tell me what to do for the project. No, you're missing the point. Just figure something out and just do something weird and fun. Whether it's here's a problem I think is interesting and I want to see if I can use evolutionary computation for it, sure. If it's I really want to learn NEAT, so I'm going to use NEAT for this particular problem, great. If you're like, I know, I'm certain I have a really good crossover that's going to work really well on this type of problem and I'm going to prove it, do it. I want you to just do whatever the hell you want. The weirder, the better. Like I was watching a video the other day and I was like, man, this would be fun if a student did this as like a project. And like often, like if any of you have talked to past students that have had me in like this class, you will know that like I don't care about its value. I care about like, oh, that's fun. That's the point of you're in university right now. In university, that's where you get to say, I don't know, that's fun. You don't need to be worried about like, can I sell this? What value does this have for my boss? It doesn't matter, just have fun. Screw around, see what you can get going, okay? Like I was watching this video where it was talking about evolutionary game theory. You probably don't, who knows what evolutionary game theory is? Yeah, right? Turns out it's pretty straightforward. You can probably learn it in a 5-minute video. But I was like, wouldn't it be kind of fun if just some student just like screwed around with evolutionary game theory? Because the evolutionary game theory like uses the ideas kind of like of evolutionary computation, but in isolation. So if someone's like, well, let's take evolutionary computation, like really throw it out. Have fun, just see what happens. If you're saying like, what do these results mean? Sometimes you don't need an answer to that. You can just say like, isn't that cool? And someone says, but what's the point? You go, it's cool. That's what I want, okay? Get creative, have fun. I don't want to be bored with any of your assignments and especially not your project. Have fun. The weirder, more interesting nonsense you can try, the better. Don't be so worried about it didn't work though. Doesn't matter. As long as like what you did wasn't obviously a dumb idea, I don't care. And when I say obviously a dumb idea, I mean like one that is like a 5-year-old could tell you that's a dumb idea. Not one that I could rationalize why that's a bad idea. Well, no, I've got some experience. You might have an idea that your average person might be like, that's a good idea, but I could be like, here's why that's a bad idea. No, if you did something that I can rationalize as a bad idea later, whatever, you tried it, who knows? But have fun, explore. If you do what I ask you to do, you're not going to have fun and you're kind of missing the point. I want you to do what I'm really asking you to do, which is screw around, have fun. All right, and that's it for today. I'll catch y'all later. Have a wonderful weekend.